This is X203, Project 5 of A4. Today we're talking about grid algorithm. The definition of grid algorithm. The approach selects the best choice at each step instead of considering all sequences that may lead to an optimal solution. So let's first consider about one example. To make change for 67 cents, we have quarter, dime, nickel, and penny, and using the least number of coins. Because 67 is greater than quarter, which is 25 cents, so we now first using quarters to make changes. We could use 2 quarters, which made it to 50 cents. And then what left is 70 cents. So 70 cents is greater than 1 dime, so we could use 1 dime. And then use the same approach, we could use 1 nickel. And then we have 2 pennies left, so we have 2 pennies. So the best choice is using 2 quarters, 1 dime, 1 nickel, and 2 penny.
Let's come to an example. To make 99 cents change with quarters, dimes, nickels, and pennies, and using the least total number of coins. To solve this problem, we need to make changes for the 99 cents. And we know that we need to start with the largest denomination, so we need to try the quarter first, which is 25 cents. We know 99 is larger or equal to 25, so we use the first quarter. And the number of changes we need to make becomes 99 minus 25, so it is 74. We find out 74 is still larger or equal to 25, so we use the second quarter, and the number here becomes 74 minus 25. It becomes 49 now. 49 is still larger or equal to 25. We use the third quarter, and the number we need to get a change becomes 49 minus 25, which is only 24. So we say 24 is no longer larger or equal to 25, so we are done with quarters. We use 3 quarters in total. We will try the next largest denomination of coins, which is a dime, 10 cents. We know 24 is larger or equal to 10, so we use our first dime. The n now becomes 24 minus 10, which is 14. We still find out 14 is still larger or equal to 10. We use our second dime, which is 14 minus 10, which is 4. We will realize we are done with the dime now, since 4 is no longer larger or equal to 10. So now we will come to nickels. Nickel is 5, but 4 is not larger or equal to 5, so no nickels. So we come to the next largest denomination of coins, which is 1. 4 is larger or equal to 1, and we will use our first cent, and it will become 3. Oh, here is pennies. And 3 is still larger or equal to 1. We use the second one, and it will become 2. 2 is still larger or equal to 1, and we use third one, which is like 2 minus 1 equal to 1. 1 is larger or equal to 1. We use the fourth penny, and we come to realize we have got all the changes we need. So in total, we get 3 quarters, 2 dimes, and 4 pennies to solve this problem.
The general procedure for this kind of problem. To make changes of n values using C1, C2 until Cr values of denominations of coins, well, C1 is greater than C2, and etc. We have a loop where at each step we have n greater than Ci we begin add coin with value Ci to the change, and we decrease the current n by Ci, and we keep going through the slope until we get to the end.
So we have another question, and it is, if you have coin denominations of 1, 5, 10, 20, 25, and 50, is the greedy algorithm optimal to make 40 cents? So we already know that the greedy algorithm, you're supposed to choose the highest denominations first. So we'll start with that. So that means we're going to use 1/4. We're going to use 1 dime and 1 nickel. So that gives us 40. We have to use 3 coins. However, because we added the 20, we could easily have just done 20 and 20 to get us 40, giving us 2 coins. So the greedy algorithm is not always optimal, but since we added the 20 denomination in that, it did not make it optimal. So our next counterexample includes a traveling salesman problem, which is known to not be optimal using the greedy algorithm. So we're going to prove it using the next picture, which means you're supposed to get from A to E, but you have to touch every single letter in between. So we're going to do it with the greedy algorithm first, and they're going to be denoted by squiggly lines. So to use the greedy algorithm to make it from A to E, we're going to go from A to B, then B to D, then D to B, B to C, and C to E. So what we had there was 2 plus 3 plus 3 plus 4 plus 4, which should equal 16. Now, using a non-greedy algorithm, we could easily have just gone from A to D, D to B, B to C, and C to E, without having to backtrack from B to D as we did in the greedy. So here we had a 3, 3, 4, 4, which ends up equaling 14. So this proves that the greedy algorithm is not optimal for the traveling salesman problem.